In 2018, astronomers discovered a galaxy that should not exist. Not in the way that hot Jupiters shouldn't exist, or diamond planets shouldn't exist, where the surprise is a violation of our formation models, a puzzle with a plausible solution waiting to be found. This was different. This was a galaxy whose existence did not just challenge a model, it challenged the invisible scaffolding that holds the entire universe together. The galaxy is called NGC 1052-DF2. It is roughly the size of the Milky Way. It contains billions of stars, arranged in the loose, diffuse structure of an ultra-diffuse galaxy, spread thin across space, dimmer than most, easy to overlook. By most measures, it is unremarkable. Except for one thing. It has almost no dark matter. And that sentence, to anyone who understands what dark matter is and what it does, reads like a description of something physically impossible, like finding a planet with no gravity or a star with no fusion. Dark matter is not a feature of galaxies. Dark matter is not something galaxies optionally contain. Dark matter, according to everything we understand about how galaxies form and survive, is what galaxies are built from. Without it, NGC 1052-DF2 should not be there. But it is, and nobody knows why. To understand why this discovery broke something fundamental, you need to understand what dark matter actually is, and more importantly, what it does. Dark matter is matter we cannot see. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation in any way we have yet detected. It is invisible not because it is far away or dim, but because it is genuinely, fundamentally transparent to every form of light we know how to use. We know it exists because of gravity. In the 1970s, astronomer Vera Rubin was measuring how fast stars orbit the centers of spiral galaxies. According to Newtonian gravity, stars at the outer edges of galaxies should orbit more slowly than stars near the center, just as the outer planets of our solar system orbit the Sun more slowly than the inner ones. The math is straightforward. The further from the gravitational center, the slower the orbit. The stars were not obeying that rule. Stars at the outer edges of galaxies were orbiting just as fast as stars near the center, sometimes faster. The rotation curves were flat when they should have been declining. The only explanation that fit the data was that there was more mass in these galaxies than the visible matter and gas could account for, mass that was not glowing, mass that was not emitting any signal, an invisible component providing extra gravitational pull that kept the outer stars moving faster than they had any right to. Dark matter. Current estimates suggest that dark matter makes up approximately 27% of the total mass energy content of the universe. Normal matter, everything we can see, everything made of atoms, every star and planet and gas cloud and person, makes up approximately 5%. Dark matter outweighs everything visible in the universe by more than 5 to 1. And in galaxies specifically, dark matter is not a minor addition, it is the dominant component. A typical galaxy like the Milky Way is embedded in a dark matter halo, an enormous, roughly spherical cloud of invisible matter extending far beyond the visible stars, providing most of the galaxy's total mass, anchoring the structure that allows the galaxy to hold together and maintain its shape. Without a dark matter halo, a galaxy should fly apart. The stars should disperse. The visible matter alone is not gravitationally sufficient to hold a galaxy together over billions of years. NGC 1052-DF2 has almost none of it. And it is still there, still intact, still holding together. The discovery was made by astronomer Peter Van Dokkum and his team at Yale University, using data from the Dragonfly Telephoto Array, a telescope specifically designed to detect extremely faint, diffuse structures that conventional telescopes miss. They were studying the neighborhood around a giant elliptical galaxy called NGC 1052 when they noticed DF2 in the background, a ghostly, sparse collection of stars that barely registered against the sky. When they measured the velocities of the globular clusters orbiting DF2, dense balls of stars that orbit galaxies the way moons orbit planets, they found something that stopped the analysis cold. The globular clusters were moving too slowly. Not slightly slowly, dramatically slowly. The velocities were consistent with the gravitational pull of the visible matter alone, the stars and gas they could see, with almost no additional pull from an invisible dark matter component. The dark matter halo that should have been there, providing 5 times the gravitational influence of the visible matter, was simply absent. Van Dokkum's team checked the analysis. They checked it again. They looked for errors in the distance measurement. If DF2 was closer than they thought, the velocities would look different. They looked for errors in the velocity measurements themselves. They published the result, braced for immediate criticism, and waited. The criticism came. Other astronomers disputed the distance estimates. Alternative analyses were published suggesting the dark matter deficit might be less extreme than the original paper claimed. And then, in 2019, Van Dokkum's team found another one, NGC 1052-DF2. Same neighborhood, same ultra-diffuse structure, same absence of dark matter. Then more, a population of dark matter-deficient galaxies, all in the same region of space, all clustered around the giant elliptical NGC 1052 like satellites of something that had stripped them of their most important component. Not one impossible galaxy, a family of them. This is where the mystery deepens in a way that keeps cosmologists awake. Because there are 2 separate problems with dark matter-deficient galaxies, and they pull in 2 different directions. The first problem is structural. How does a galaxy survive without dark matter? If dark matter is what holds galaxies together, then DF2 and DF4 should have dispersed long ago. Their stars should have drifted apart over billions of years, the galaxy dissolving into a loose scattering of stars with no coherent structure. But they haven't. They are still there, still recognizable as galaxies, still holding a shape. The second problem is formational. How did a galaxy form without dark matter in the first place? The standard model of galaxy formation, Lambda-CDM, the model that underlies virtually all of modern cosmology, says that galaxies form inside dark matter halos. The dark matter collapses first, under its own gravity, forming a halo. Then normal matter falls into that halo and forms stars. The dark matter halo is the seed. Without it, the galaxy should not have formed at all. So DF2 and DF4 are impossible twice over. They should not have formed, and even if they had, they should not have survived. The leading explanation involves the giant elliptical NGC 1052 at the center of the group.
The hypothesis is called tidal stripping. The idea is that DF2 and DF4 were once normal galaxies, dark matter halos and all, that had the misfortune of passing too close to the gravitational influence of NGC 1052. As they passed, the tidal forces of the larger galaxy, gravitational differentials that pull more strongly on the near side than the far side, stripped material away, preferentially the dark matter, which is distributed in a diffuse extended halo and is therefore more vulnerable to tidal stripping than the more centrally concentrated visible stars. The visible matter stayed. The dark matter was stripped away and absorbed into the larger galaxy or dispersed into the surrounding space. It is a plausible mechanism. Tidal stripping is real. We observe it in galaxy clusters, where large galaxies are known to cannibalize smaller ones and strip their outer components. The geometry of DF2 and DF4's situation, with both galaxies sitting near NGC 1052, is at least consistent with this explanation. But the explanation has problems. The timing is difficult. Stripping enough dark matter to reduce a galaxy to DF2's levels while leaving the stellar component intact and structured requires a very specific set of conditions: the right approach angle, the right velocity, the right mass ratio. Models can produce this outcome, but only in a narrow range of scenarios. And more fundamentally, the explanation does not address why there appears to be a population of these galaxies in the same region. Tidal stripping should be a rare event, producing occasional dark matter-poor galaxies in specific circumstances. Finding a cluster of them suggests something more systematic, something about the environment around NGC 1052 that produces dark matter-deficient galaxies at a rate that coincidence does not comfortably explain. But here is the layer of this story that goes deeper than the puzzle of one unusual galaxy group. The existence of dark matter-deficient galaxies has become ammunition in a debate that has been simmering at the edges of cosmology for decades. The debate is about whether dark matter exists at all. Not as a fringe position, as a serious scientific alternative. A class of theories called Modified Newtonian Dynamics, MOND, and its relativistic extensions proposes that what we interpret as the gravitational effect of invisible dark matter is actually a modification of gravity itself. That at very low accelerations, the kind experienced by stars at the outer edges of galaxies, gravity behaves differently from what Newton and Einstein predicted. MOND was proposed by physicist Mordechai Milgram in 1983. For decades, it was considered a minority view, useful for explaining certain galactic rotation curves, but unable to account for larger-scale phenomena like the cosmic microwave background and the large-scale structure of the universe, which dark matter models explain well.
But dark matter-deficient galaxies cut both ways. On one hand, their existence seems to support dark matter. If dark matter is real and can be physically stripped from a galaxy, that implies it is a real substance that exists separately from normal matter. You cannot strip something that does not exist. On the other hand, MOND proponents argue that the existence of galaxies with wildly varying dark matter content, from normal galaxies with expected dark matter halos to DF2 and DF4 with almost none, is harder to explain in a dark matter framework than a modified gravity framework. In modified gravity, what looks like dark matter is a consequence of how gravity behaves, not a separate substance. And the variations we observe reflect variations in the gravitational environment, not variations in an invisible component. Neither side has won this argument. Neither side has a complete explanation for all the observations. And NGC 1052-DF2 sits at the center of that argument, a galaxy that each side claims as evidence that neither side fully explains, that continues to exist in stubborn defiance of the theoretical frameworks competing to account for it. In 2023, the James Webb Space Telescope turned its attention to the NGC 1052 group. Its infrared sensitivity and resolution allowed astronomers to measure the stellar populations of DF2 and DF4 with unprecedented precision, determining the ages of the stars, their chemical compositions, the history of star formation in each galaxy. What JWST found added another layer of strangeness. The stars in DF2 are old, very old. Star formation in the galaxy appears to have stopped approximately 10 billion years ago, shortly after the galaxy formed. Something cut off the gas supply that would have allowed new stars to be born early in the galaxy's history, and the galaxy has been coasting on its existing stellar population ever since. This is consistent with tidal stripping. If the interaction with NGC 1052 removed not just dark matter, but also the gas reservoir needed for star formation, the galaxy would have stopped making new stars at the moment of the encounter. But it raises a new question. If the interaction happened 10 billion years ago, how has DF2 survived intact for 10 billion years without dark matter? 10 billion years is a long time for a galaxy held together only by the gravity of its visible stars. The simulations suggest it should have dispersed by now. It has not. Something is holding it together that the models are not fully capturing. Or the models are wrong about how quickly a dark matter-poor galaxy disperses. Or there is more dark matter than the current measurements suggest, hidden in a form or distribution that the analysis has not accounted for. We do not know which. Dark matter has never been directly detected. Decades of experiments, underground detectors filled with liquid xenon waiting for a dark matter particle to interact with normal matter and produce a measurable signal, particle accelerators attempting to produce dark matter particles in high-energy collisions, space-based instruments scanning for gamma rays produced by dark matter annihilation have produced no confirmed detection. We know dark matter's gravitational effects with extraordinary precision. We have mapped its distribution across the universe using gravitational lensing. We have simulated the formation of cosmic structure and confirmed that a dark matter component is necessary to reproduce what we observe. But we have never held a dark matter particle, never measured one directly, never confirmed what it actually is. And then along comes a galaxy that apparently has none of it and keeps existing anyway. The universe has a way of doing this. Every time we construct a framework, a model that explains what we observe, that makes predictions we can test, that gives us the satisfying feeling of understanding, the universe finds something that sits just outside the framework's edge and refuses to fit neatly inside it. Dark matter is the invisible foundation of modern cosmology. It is in the textbooks, it is in the simulations, it is in the calculations that successfully predict the large-scale structure of the universe, the temperature fluctuations in the cosmic microwave background, the behavior of galaxy clusters under gravitational lensing. It is the most successful invisible thing in the history of science. And there's a galaxy 212 million light-years away that apparently has none of it, that formed without it, or lost it, or exists in some state our models have not fully described, that sits in a group of similar galaxies, all of them defying the same expectation, all of them orbiting a giant elliptical that may or may not have something to do with why they are the way they are. NGC 1052-DF2 does not disprove dark matter. The evidence for dark matter, taken as a whole, remains overwhelming. But it does something almost more unsettling than disproving it. It reveals a gap, a place where the framework doesn't quite reach, a galaxy-shaped hole in our understanding of the most abundant form of matter in the universe, a substance we have spent decades studying and still cannot touch, still cannot see, still cannot catch in any detector we have ever built. We mapped the invisible scaffolding of the cosmos, and then we found a building that somehow forgot to use it. Still standing, still there, still waiting for an explanation that for now, the universe has declined to provide.